The terrifying journey through the center of a spinning black hole. Tonight, I want to take you somewhere that nobody has ever been and nobody ever will. A spinning black hole does not have a center the way most people imagine. It does not end in a point. It does not contain one horizon. If the equations are followed far enough, it turns the center into a ring, and then asks whether space, time, and cause still mean anything at all. Get comfortable. Pull a blanket up if there is one nearby. Let the lights go a little softer. We have a long, slow walk ahead. If the slow stories of the cosmos are the kind you keep coming back to, a quiet subscribe means a great deal here. Now, let's begin. The first thing I want to say, and I want to say it carefully, is that the picture of a black hole most of us carry in our heads is wrong. Not wrong in a dramatic, shocking way. Wrong in a quiet, structural way that matters once you start asking honest questions about the inside. The standard picture is something like this. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape. At its edge is the event horizon, a one-way membrane. Inside, somewhere at the center, is a singularity, a point of infinite density where the equations of general relativity stop making sense. You fall in. You get pulled apart by tidal forces. You reach the singularity. The story ends. That picture is a description of a particular kind of black hole. It is called a Schwarzschild black hole, named after Karl Schwarzschild, who was a German physicist who solved Einstein's field equations for a non-rotating, uncharged sphere of mass in late 1915, while serving on the Eastern Front of the First World War. He sent the solution to Einstein in a letter in December of that year. He died a few months later, in May 1916, from an autoimmune disease he had contracted at the front. His solution was the first exact answer general relativity had ever produced, and for almost 50 years, it was the only one anyone had for the interior of a black hole. A Schwarzschild black hole is mathematically clean and physically simple. It has only one property, mass. It does not rotate. It does not carry any electric charge. It is perfectly spherical. The singularity at its center is, in the mathematical idealization, a single point. Everything that falls and moves toward that point along a one-way trajectory and is destroyed there. That is the picture in every undergraduate physics textbook. It is the picture in almost every popular science article you have ever read about black holes. It is the picture you almost certainly have in your head right now. The problem is that this kind of black hole almost certainly does not exist in our universe. Real things in space rotate. Stars rotate. The clouds of gas that collapse into stars rotate. Planets rotate. Galaxies rotate. There's a principle in physics called the conservation of angular momentum, which says that if something is spinning and you compress it, it has to spin faster, the way a figure skater pulls in their arms during a spin and accelerates. When a massive star collapses at the end of its life, the collapse compresses an object that was already rotating, and the result is something that rotates extraordinarily fast. Real astrophysical black holes, the ones we actually find in the universe, are spinning, often at speeds close to the maximum theoretical limit allowed by general relativity. In 1963, a New Zealand mathematician named Kerr found the exact solution to Einstein's equations for a rotating black hole. He had been working on the problem for months, in a small office at the University of Texas. The solution came to him in pieces, partly through inspiration, and partly through one of the most difficult sequences of algebra in the history of theoretical physics. When he finally wrote it down, the equations that emerged described an object that was, in many specific ways, fundamentally different from the Schwarzschild black hole everyone had been studying. For nearly 50 years, the Schwarzschild solution had been the only exact answer general relativity had ever produced for a black hole. Kerr's solution was the second, and it described a much stranger object. The story of how Kerr found the solution is itself worth a moment, because it illustrates something about how this kind of physics gets done. He had been studying the algebraic structure of the equations, looking for solutions with the particular kind of symmetry, and he had been making slow progress for the better part of a year. The breakthrough came when he tried a specific algebraic ansatz, a guess at the form of the answer, that had a particular kind of internal consistency. The guess worked. The algebra collapsed into a manageable form, and the equations began to yield a solution that no one had seen before. When Kerr first presented the result at a conference in 1963, some of the senior physicists in the audience did not believe him, in part because the result was so unexpected, and in part because the algebra was so complicated that it was hard to verify on the spot. The solution survived all subsequent verification. It is now one of the cornerstones of modern general relativity. The Kerr black hole has a different interior structure. Its singularity is not a point. Its event horizon is not the only horizon. Space and time inside it do strange things they do not do inside a non-rotating black hole. The center of a spinning black hole, mathematically, is not a place. It is a region, with a shape, with paths through it, and with possibilities that the simpler Schwarzschild model never allowed. That is what we are going to walk through tonight. The interior of a Kerr black hole. The real kind. The kind that almost certainly exists somewhere in our galaxy at this very moment. The journey is layer by layer, and each layer is stranger than the one before it. Some of them you may have heard of in passing. Most of them you probably have not. By the time we reach the center, you will understand why physicists, when they talk about the inside of a real black hole, often pause before answering and choose their words very carefully. Before we approach the black hole itself, I want to spend a moment on why this matters. Why almost every black hole you have ever heard about is, almost certainly, a spinning one. There is a result in general relativity called the no-hair theorem. The name is a joke, but the physics is serious. The theorem says that a black hole, once it has formed and settled down, can only have three properties: mass, electric charge, and angular momentum, which is to say, spin. Everything else about whatever fell in to form the black hole, every detail of its composition, its temperature, its history, every individual star or atom is lost. It does not show up on the outside in any way. The black hole, as far as the rest of the universe can tell, is described by three numbers and nothing else. Of those three numbers, electric charge is essentially always zero in any realistic astrophysical black hole. Charged matter in space attracts opposite charges very quickly and neutralizes itself. So in practice, real black holes have only two relevant properties: mass and spin. That means the only meaningful difference between two black holes of the same mass is how fast they are spinning. And almost all of them are spinning fast. Consider what has to happen for a black hole to form. The most common way is the collapse of a massive star at the end of its life. The star runs out of fuel. The outer layers explode outward in a supernova. The core, what is left of it, collapses inward under its own gravity. If the core is heavy enough, the collapse does not stop at a neutron star. It continues all the way down, until everything that was the core is inside its own event horizon, and a black hole has formed. Now, that core was already rotating before the collapse. Stars rotate. The sun rotates with a period of roughly 25 days at its equator. More massive stars often rotate faster. When the core collapses, it gets dramatically smaller. Its radius might shrink by a factor of 100,000 or more. The conservation of angular momentum says that as the radius shrinks, the rotation rate has to increase to compensate. The result is an object that is rotating extraordinarily fast, often close to the theoretical maximum that general relativity allows. The maximum rotation rate of a Kerr black hole is set by a parameter called the spin parameter, which has a value between 0 and 1. 0 is no rotation, the Schwarzschild case. 1 is the maximum possible rotation, the so-called extremal Kerr black hole. Real measurements of black holes in our galaxy have found spin parameters around 0.8, 0.9, sometimes higher. We have measured these spins by looking at how the X-ray light from the matter near the black hole is shifted and distorted. The fact that we can do this measurement at all is one of the more impressive achievements of modern observational astrophysics. Let me explain briefly how that measurement is done, because it illustrates how much of what we know about black holes comes from indirect evidence. Matter falling into a black hole, in the accretion disk, gets very hot and emits X-rays. The innermost stable orbit of that matter, the closest it can get to the black hole before falling in, depends sensitively on the spin of the black hole. A non-rotating black hole has its innermost stable orbit at a particular distance. A maximally rotating black hole has its innermost stable orbit much closer in. By measuring the X-ray spectrum from the inner edge of the accretion disk, and looking at how the iron emission line is broadened and shifted by the gravitational field, we can work backward to determine where the inner edge actually is, and from that, what the spin of the black hole must be. This is how we know that the black hole at the heart of the binary system GRS 1915 plus 105 has a spin parameter that has been measured to be very close to the theoretical maximum, in some studies above 0.98. This is how we know that several supermassive black holes in nearby galaxies are spinning at near extremal rates. The measurements are difficult, the systematic uncertainties are real, but the conclusion is robust. Real black holes spin. Most of them spin fast. The point is, when you imagine a black hole, the picture you should have in your head is not a still, perfectly spherical object. It is a wildly spinning region of space-time, dragging the universe around with it as it goes. That dragging, as we will see, is the first of the layers we have to pass through to reach the center. But before we get to that, there is a region around the black hole that is, in a sense, the surface where everything else in the universe goes to die. We have to cross it first. A real black hole in space is almost never alone. It usually has a companion, a star or a cloud of gas, and the gravity of the black hole slowly pulls material in from that companion. The material does not fall straight in. Because it has angular momentum, it spirals inward, forming a flattened disk of gas around the black hole called an accretion disk. The accretion disk is one of the most extreme environments in the known universe. The gas in it orbits the black hole at speeds that approach the speed of light. As different layers of the disk move at slightly different speeds, they rub against each other. That friction, on this scale, generates temperatures of millions of degrees. The disk glows. It glows so brightly that the matter falling into the most massive black holes in the universe outshines entire galaxies. This is what a quasar is. It is light from an accretion disk. If you were approaching a real spinning black hole, the disk would be the first thing you saw. Long before you reached the event horizon, you would see a vast, bright, flat structure of glowing gas, twisted and warped by the black hole's gravity in ways that no other object in the universe can produce. The light from the far side of the disk, the part behind the black hole from your point of view, would not be hidden. It would be lifted up, bent over the top and the bottom of the black hole by the gravitational lensing of the spacetime curvature, and would appear to you as two glowing arcs above and below the dark center. The actual shape of the black hole's silhouette would not be circular. It would be slightly distorted, slightly oval, because the rotation of the black hole drags the spacetime around it asymmetrically. You would also notice that time itself is starting to behave strangely as you approach. Light from objects far behind you, the rest of the universe, would appear blue-shifted, compressed, sped up. Light from objects on the disk would appear to slow down and stretch out. Clocks would run at different rates, depending on which direction you looked. This is the outermost layer of the descent. We have not even reached anything that is unique to a spinning black hole yet. Everything in this section happens around any black hole. But as you get closer, the rotation begins to assert itself. The space around the black hole starts to do something that no static black hole can do. It starts to move, all on its own. The next layer, the first one that exists only because the black hole is spinning, is called the ergosphere. The name comes from the Greek word ergon, which means work, because in this region, the spinning of the black hole can do work on objects that enter it. It can give them energy, or take energy from them, depending on how they move. The ergosphere is the region of space around a Kerr black hole where the rotation of the black hole drags the fabric of spacetime itself faster than the speed of light, in the direction of rotation. This is called frame dragging. It is a real, measured effect, predicted by general relativity in the 1910s and finally measured in the early 2000s by a satellite experiment called Gravity Probe B, which detected the frame dragging caused by Earth's rotation. Earth's frame dragging is tiny. The Earth is barely spinning on the relevant scale. The frame dragging around a black hole is so strong that the very space inside the ergosphere is being carried around the black hole faster than light can travel through it. Let me unpack what that actually means, because it is one of the most counterintuitive consequences of general relativity, and it gets glossed over in almost every casual description of black holes. In the ordinary universe, far from any massive object, you can stand still. You can find a frame of reference in which you are not moving, in which the stars appear stationary, in which time passes for you at a steady rate. This is what we call being at rest. It is the default state we all live in. Most of physics, in some sense, is built around the idea that there is always such a frame available, no matter where you are. Inside the ergosphere of a Kerr black hole, that frame does not exist. There is no possible state of motion that corresponds to standing still relative to the distant stars. Every observer inside the ergosphere, no matter how powerful their engines, no matter how clever their trajectory, is being carried around the black hole. The space they occupy is itself moving, and moving in a way that they cannot resist. What this means, practically, is that no object inside the ergosphere can stand still, not relative to a distant observer, not relative to a fixed star, not relative to anything. The space the object is sitting in is itself moving, and moving so fast that no possible thrust, no possible engine, no possible force in the universe could push the object hard enough to remain stationary. Inside the ergosphere, you must rotate with the black hole. There is no other option. You can still escape the ergosphere. You have not crossed any horizon. You can fly back out into the universe, if your trajectory is right and your engines are powerful. But while you are inside it, you are caught in the rotation. The black hole is, in a real sense, dragging you around with it, and there is nothing you can do about it. There is something even stranger. The ergosphere has a shape. The outer edge is called the static limit, and the inner edge is the outer event horizon. The static limit is shaped like an oblate spheroid, wider at the equator than at the poles, like a slightly squashed sphere. The shape comes from the fact that frame dragging is strongest near the equator of the rotating black hole and weakest near the poles. So the ergosphere is thicker near the equator. If you approach the black hole along its rotation axis, the ergosphere is thinner. If you approach it along the equator, you are inside the ergosphere long before you would otherwise expect. The ergosphere is also where the black hole's astonishing brightness, in real astrophysical systems, ultimately comes from. The matter falling in from the accretion disk, when it crosses the static limit, gets spun up by the drag spacetime. Some of that material is funneled into thin, energetic jets that shoot out from the rotation axis of the black hole at nearly the speed of light. The jets are visible across the universe. They are the brightest single objects we can see in the sky, in some wavelengths, and they are powered, ultimately, by the rotation of the black hole, transmitted through the ergosphere to the matter that passes through it. There's one more thing to know about the ergosphere before we cross deeper. It is possible, in principle, to extract energy from a spinning black hole by sending an object into the ergosphere on a particular kind of trajectory and letting it split into two pieces. One piece falls into the black hole. The other piece comes back out, but with more energy than the original object had going in. This is called the Penrose process, after Roger Penrose, who described it in 1969. The energy comes from the rotation of the black hole itself. The process slows the black hole down, very slightly, every time it happens. In principle, you could mine a spinning black hole for energy this way, until it stops spinning, at which point it would be a Schwarzschild black hole, and no further energy could be extracted. That is a consequence of the ergosphere. It is the first place where the spinning of the black hole shows up as a real, physical, observable effect. And we have not even reached the event horizon yet. Past the inner edge of the ergosphere, however, the rules change again. And the next change is the most important one in the entire descent. Once you cross the next surface, you stop being part of the universe in any way that the universe outside can observe. The outer event horizon of a Kerr black hole is, in many ways, similar to the event horizon of a non-rotating black hole. It is the surface beyond which nothing, not even light, can ever return to the outside universe. Once you cross it, you are inside the black hole. You will not come out. There is no possible trajectory, no engine, no escape. But the way the horizon behaves at the moment of crossing is, in another way, much stranger than people often realize. If the black hole is large enough, you would not feel anything when you crossed it. There is no wall. There is no sound. There is no flash of light. The event horizon is not a physical surface. It is a mathematical boundary defined by the geometry of spacetime. From your perspective, you would simply continue falling inward. You might not even know, at the moment of crossing, that you had crossed. A small black hole, the kind formed by the collapse of a single massive star, would kill you long before you reached its event horizon. The tidal forces, the difference in gravity between your head and your feet, would be so extreme that you would be stretched into a thin column of atoms, a process unfortunately named spaghettification. For a stellar mass black hole, this happens far outside the horizon. You would never make it to the inside. But for a supermassive black hole, the kind found at the center of galaxies, the situation is different. The gravity gradient at the event horizon of a supermassive black hole is gentle. You could cross it alive, intact, conscious, without feeling any unusual force at all. The horizon of the supermassive black hole at the center of our own galaxy, the one we call Sagittarius A star, has a gravitational gradient that you, as a human body, would not be able to detect. You could cross it without knowing. What you would notice, however, is something happening to the universe behind you. As you fall toward the horizon, light from the outside universe behaves in increasingly strange ways, depending on your path and the geometry of the black hole. Some of it gets blue-shifted as it catches up to you. Some of it gets distorted by the curvature of space-time around the rotating mass. The view of the universe behind you would not look normal. It would be compressed, shifted, twisted, in patterns that depend on the angle of your approach and the spin of the hole. But I want to be careful here, because there is a popular version of this idea that is wrong, and it has been repeated for decades in places that should know better. The popular version says that as you fall toward the event horizon, you would see the entire future history of the universe play out behind you, compressed into a single moment of brilliant blue-shifted light before you crossed. That is not what general relativity actually predicts. An infalling observer crosses the event horizon in finite proper time, on their own clock, and they do not have time to receive light from the entire infinite future of the outside universe before they cross. The popular image of watching all of cosmic history flash past you in the moment of crossing is a common overstatement. It is not what the equations say. What the equations actually say is more subtle, and in some ways more interesting. The horizon is not a theater showing the end of time. It is a boundary in causality. Once you cross it, every possible future-directed path you can take leads deeper inward, toward the center of the black hole. The thing that defines the horizon is not what you see, but what you can no longer reach. Outside the horizon, the rest of the universe is in your possible future. Inside the horizon, it is not. That, more than any visual effect, is the fundamental change at the moment of crossing. That is the first piece of the title's promise. Time, as you cross into the black hole, has done something to your relationship with the outside universe that no other object in physics can do. The outside has not vanished. It is still there, but the structure of cause and effect, the network of paths you might still take into the future, no longer includes any of it. But the strangest thing happens right after you cross the horizon. The roles of space and time, in the equations describing the geometry inside the black hole, swap places. This is where we have to slow down, because the next idea is genuinely difficult, and the temptation to overstate it is enormous. Inside the outer event horizon of a Kerr black hole, there is a region of spacetime where, in the mathematical description, the coordinate that used to behave like a spatial direction now behaves like time, and the coordinate that used to behave like time now behaves like a spatial direction. This is what physicists mean when they say that, inside a black hole, space and time exchange roles. Let me unpack what that actually means, because it sounds more dramatic than it is, and at the same time, it is more strange than it sounds. Outside a black hole, you can choose to move in any direction in space. You can go forward, backward, left, right, up, down. You cannot, however, choose to move in time. Time only goes one way. You can travel through space at will. You cannot travel through time, except forward, at the rate of 1 second per second. This is so basic to our experience that we do not even think of it as a feature of physics. We just call it reality. Space is the thing you can move through. Time is the thing you have to live through. Inside the outer event horizon of a Kerr black hole, in the region between the outer horizon and the inner horizon, that distinction breaks down in a very specific way. The radial direction, the direction toward the center of the black hole, behaves like time. You cannot choose not to move in that direction, in the same way that, outside, you cannot choose not to move forward in time. Falling toward the center of the black hole is, in this region, like the passage of time itself. It is not optional. It is not something you can resist. It is the direction in which the future lies. What used to be your time coordinate, the dimension that ran one way and could not be reversed, now behaves like a spatial direction. You can, in principle, move forward and backward in it. You can change your speed in it. It is just another dimension you can navigate. You could, if you somehow had the engines to do it, travel back and forth along the dimension that used to be your time, the way you used to travel back and forth in space. This is what I mean when I say the title's promise about time is more honest than it might first sound. Inside the black hole, in this region, the structure of time and space is not what it is outside. The two have swapped roles. Falling is unstoppable. The thing that used to be unstoppable, the forward motion of time, is no longer the same kind of thing. You cannot stop falling, in this region, for the same deep reason that you cannot stop time. The two have, mathematically, become the same kind of thing. The future is at the center. This is one of the genuine consequences of general relativity at this scale. It is in every textbook on black hole physics. It is why no object inside the outer event horizon can ever come back out. It would have to move backward in what is now a time-like direction, and the universe does not allow that. The thing we call the unidirectionality of time, the fact that the future cannot be revisited, has, inside the black hole, become the unidirectionality of inward motion. The center is the future. Falling is forward. There is no other direction to go. You have crossed the outer event horizon. You are falling toward the center of the black hole. But in the deepest sense, you are falling into the future of the inside of the black hole. There is no stopping. There is no turning around. But ahead of you, and getting closer, there is another horizon. And what happens there is, in many ways, worse than what happens at the center itself. The inner horizon of a Kerr black hole has a name that physicists use almost as a kind of warning. It is called the Cauchy horizon, after the 19th century French mathematician Augustin-Louis Cauchy, who studied the question of when the future of a system can be uniquely predicted from its present state. The Cauchy horizon, in the context of a black hole, is the boundary beyond which the future is no longer uniquely determined. Past this surface, the equations of general relativity stop being able to predict what will happen, even in principle. Let me explain what that means in physical terms. In normal physics, in the world outside black holes, if you know the state of a system at one moment, the laws of physics tell you what will happen next. You may not know it precisely, in practice, but in principle the future is determined. This is what we mean when we say that physics is deterministic, in the classical sense. Inside the outer horizon of a Kerr black hole, in the region we just discussed, this is still true. The equations work. The future, although confined to the inside of the hole, is still predictable from the present state. At the Cauchy horizon, this guarantee fails. The equations no longer have a unique solution past the horizon. You can solve them in different ways, and you get different futures, all of which are mathematically valid. The horizon is the boundary of predictability itself. It is, in a sense, where the rules of the game stop being clear. When Roger Penrose and Stephen Hawking developed the singularity theorems in the 1960s, the Cauchy horizon was one of the most troubling features they found. It seemed to suggest that something genuinely non-deterministic could happen inside a real black hole. Either the laws of physics change at the Cauchy horizon, or the horizon does not really exist in any realistic black hole, or something else, something not yet understood, intervenes before the horizon is reached. For a long time, the prevailing view was that the Cauchy horizon was a mathematical artifact of the perfectly clean, idealized Kerr solution, and that any realistic black hole, with even a tiny amount of mess in its history, would not have a true Cauchy horizon at all. Something would prevent it from forming. The horizon would, in some sense, be destroyed by the same realistic perturbations that would otherwise reach it. That intuition turned out to be correct. The Cauchy horizon does not survive in any realistic black hole, but the way it gets destroyed is, perhaps, the most violent process we know of in pure gravitational physics. It is called mass inflation, And it is the thing that actually kills you inside a real spinning black hole. Not the singularity, not the falling, not the tidal forces. Something else, hiding at the inner horizon, that almost no popular description of black holes has ever told you about. I want to spend some time on this because, in a sense, mass inflation is the real terror at the heart of a spinning black hole, more than the ring singularity itself, more than the strangeness of swapped coordinates, more than anything else inside. Imagine you are inside the outer horizon of a Kerr black hole, falling toward the inner horizon. The Cauchy horizon is ahead of you. Mathematically, the geometry says you should reach it, cross it, and continue inward toward the ring singularity. In a perfectly clean, mathematically idealized Kerr black hole, you would reach the Cauchy horizon and pass through. Some descriptions of black hole interiors stop here and tell you that the inner horizon is just another horizon, a strange one, but ultimately just another mathematical surface you can cross. That picture is wrong, and it is wrong in a way that matters. The universe is not mathematically clean. Stuff has fallen into this black hole. Photons, atoms, cosmic rays, other objects, maybe a little gravitational radiation from a passing star. All of it falls in, and all of it ends up, eventually, near the inner horizon. Here is the problem. As objects approach the inner horizon, the gravitational blue shift becomes infinite. Light that fell in shortly after the black hole formed has been falling for a very long time, and as it approaches the Cauchy horizon, the blue shift compresses its energy by an enormous factor. By the time it reaches the horizon, the energy of that light, in the frame of an observer at the horizon, is, in the idealization, infinite. That is not a metaphor. That is what the equations say. The energy of any infalling radiation, evaluated at the inner horizon, blows up to infinity. Now, infinite energy creates infinite gravity. Gravity bends spacetime. If the energy at the inner horizon is unbounded, the curvature of spacetime there is unbounded. The smooth, well-behaved geometry of the idealized Kerr solution is destroyed by the very matter that fell into the black hole. The inner horizon, in the realistic case, is not a horizon at all. It is a curvature singularity, a place where spacetime itself is torn. This effect is called mass inflation, because the effective mass of the inner region appears, from the inside, to inflate without bound as you approach the Cauchy horizon. It was first described in detail by Eric Poisson and Werner Israel in 1990, and it has been confirmed by every subsequent calculation. In any black hole that has ever absorbed any matter or radiation, which is to say, in every real black hole, the inner horizon is destroyed by mass inflation before any infalling observer can reach it. Recent numerical simulations, using more sophisticated methods, have only strengthened this conclusion. The inner horizon is fragile. It does not survive contact with reality. So the terrifying truth about the inside of a spinning black hole is not the ring singularity. The ring singularity, in the clean Kerr solution, is a strange and beautiful object that you can, in principle, navigate around. The thing that actually destroys you is the inner horizon, where the entire history of the universe outside the black hole has been blue-shifted to infinite energy and concentrated into a single, violent, instantaneous event. Think about that for a moment. Everything that fell into the black hole, every photon of starlight that was captured, every atom of gas that drifted in from the accretion disk, every cosmic ray and gravitational wave and particle of dark matter, all of it has been falling toward the inner horizon for as long as the black hole has existed. And from your perspective, as you approach the inner horizon yourself, all of it arrives at the same moment, all of it simultaneously, at infinite energy. The mass inflation singularity is, in a sense, where the entire infalling history of the black hole is compressed into a single point in your future. You would not see it as a wall, or a flash, or a force. You would not see it at all. By the time the light from it reached you, that light would have already been so blue-shifted, so concentrated, so violent, that it would not be light anymore. It would be a region of pure curvature, where the mathematical structure of spacetime itself fails. You would not survive this. Nothing physical would. The infinite blue shift would tear apart any object made of atoms, any photon, any field, anything that exists. The Cauchy horizon is, in any real black hole, a wall of compressed, infinitely energetic radiation that has been falling toward you for the entire history of the black hole, all of it arriving at the same moment from your perspective. That is the killer. That is the actual end of the journey. And any black hole that has ever existed in the real universe. Not the ring at the center, the blue shifted radiation at the inner horizon, but mathematically, in the idealized solution, the journey continues. And what waits past the inner horizon is, if anything, even stranger. In the clean Kerr metric, if you somehow survived the inner horizon, something remarkable would happen on the other side. The roles of space and time, which had swapped at the outer event horizon, would swap back. Inside the inner horizon, in this picture, the radial direction once again behaves like a spatial direction, and time once again behaves like time. You can choose to move toward the center of the black hole or away from it. You can stop. You can hover. You can orbit. The future is no longer pinned to a particular direction in space. The geometry in this region is closer to the geometry of the universe outside a black hole than to the geometry of the region between the two horizons. This is a strange and important fact about Kerr black holes that is missing from most casual descriptions. Inside a non-rotating Schwarzschild black hole, there's only one horizon, only one space-time swap, and you fall, helplessly, to the singularity. Inside a Kerr black hole, the equations describe two horizons. The swap happens twice, and beyond the second one, you are free again. You can avoid the singularity. You can navigate around it. In the clean mathematical picture, the inside of a Kerr black hole has a region where you can choose your path. All of this assumes the idealized picture. In any real black hole, mass inflation has destroyed the inner horizon, and you cannot reach this region. But the mathematics of it is real. The equations describe a part of the spacetime that, if it existed in pure form, would allow choices and motions that are impossible in the simpler model. It also means that the singularity at the center is approachable in a different way than people usually imagine. You do not fall onto it inevitably. You can, in the clean geometry, look at it, orbit it, choose to stay away from it. The center is no longer the inevitable destination. It is a place, and the place has a shape. The center of a spinning black hole, in the clean Kerr geometry, is not a point. It is a ring. The ring lies in the equatorial plane of the rotating black hole, at a finite radius determined by the black hole's mass and spin. For a stellar mass black hole spinning at near maximum rate, the ring would have a radius of a few kilometers. For a supermassive black hole, the ring would be much larger, potentially the size of a small star. This is a feature of the idealized Kerr metric that almost everyone gets wrong when they first hear about black holes. The textbook image of a singularity as a point of infinite density is the Schwarzschild image, the one that exists only when the black hole is not rotating. As soon as the black hole has any spin at all, the singularity is no longer a point. It is a ring, and the ring has properties that a point singularity cannot have. The ring is, in the mathematical language, a time-like singularity. That phrase has a specific meaning. The ring, unlike the Schwarzschild point, is not in the future of every observer who falls into the black hole. You can, in the clean idealization, miss the ring. You can pass to one side of it. You can fly through the equatorial plane on a trajectory that does not intersect the ring at all. The ring is not your inescapable destination, the way the central point of a Schwarzschild black hole is. It is, mathematically, an obstacle in space, not in time. You also cannot easily approach it from above or below the equatorial plane in the same way. The geometry near the ring is bent in such a way that an observer approaching from a non-equatorial direction would feel a different gravitational landscape than one approaching from the equator. The ring has, in some senses, a top and a bottom and an inside and an outside, all of which are accessible by different paths. That last point, the fact that the ring has an inside, leads to one of the strangest features of the Kerr solution. If you pass through the inside of the ring, in the mathematical idealization, you do not arrive at the same kind of space you came from. You arrive somewhere else, and the equations describing what waits in that somewhere else contain a feature that, when physicists first noticed it in 1963, was so disturbing that some of them refused to believe the mathematics could be correct. Near the ring singularity, in the Kerr geometry, the equations of spacetime allow for paths that, if you trace them carefully, would return you to your own past. These are called closed time-like curves. A closed time-like curve is a path through space-time that loops back on itself. An observer following the curve would, at some point, find themselves at an earlier moment than they started. They would meet themselves. They would, in the strictest mathematical sense, travel backward in time. This is what people mean when they say that the inside of a spinning black hole permits time travel. The mathematics genuinely allows it. The equations of general relativity, near the ring of a Kerr black hole, contain paths that go back in time. This is not a trick of interpretation. It is a structural feature of the geometry. There are three things to keep straight here, because the temptation to overstate this is enormous, and the truth is more interesting than the overstatement. First, the closed time-like curves exist in a region of spacetime that, in any real black hole, you cannot reach. The mass inflation at the inner horizon destroys the geometry before you ever get close. The closed time-like curves are a feature of the idealized solution, not the realistic interior of any actual astrophysical black hole. So even in the most generous interpretation of the mathematics, the time travel paths are inside a region that is, in any realistic black hole, replaced by a violent curvature singularity. You would not, in a literal physical sense, ever stand at a point near the ring and choose to travel back in time, because the ring as described by the clean Kerr metric is not what is actually there in any black hole that has ever formed. Second, even in the idealization, the closed time-like curves are not stable. Small perturbations to the geometry tend to destroy them. The mathematics of general relativity allows them, but the physics of any realistic spacetime would prevent them from existing in any sustained form. Stephen Hawking proposed what he called the chronology protection conjecture, the idea that the laws of physics, in some way we have not yet fully understood, prevent the formation of closed time-like curves on macroscopic scales. The conjecture has not been proven, but it has been supported by every detailed calculation that has been done. Whenever someone tries to construct a stable region of closed time-like curves in a realistic spacetime, something goes wrong. Quantum effects diverge. Vacuum energy blows up. The geometry breaks. The universe, in some way, seems to refuse them. Third, no actual time travel that any human observer could perform has ever been demonstrated, even mathematically, in a way that respects causality. Closed time-like curves, when you trace them carefully, lead to logical paradoxes that no consistent physical theory has been able to resolve. The grandfather paradox, the bootstrap paradox, the predestination paradox, all of these arise from any honest attempt to use a closed time-like curve to do anything that affects the past. The mathematics permits the loops, but no one has been able to construct a self-consistent physics on top of them. What is true is this: the pure mathematics of a rotating black hole, taken at face value and pushed to its conclusion, contains paths that loop back on themselves in time. This was discovered by Kerr in 1963 and has been part of the formal mathematical landscape ever since. It is one of the reasons many physicists believe that general relativity must, in some way, be incomplete. A theory that allows time travel near a real, physical object, without something stopping it, is a theory that has reached the edge of its own validity. The closed time-like curves around the ring are, in this sense, less a description of reality and more a signpost. They say, here, the equations are predicting something that should not be possible, and we do not yet know what stops them. This is one of the genuine puzzles at the heart of the spinning black hole interior. The mathematics is clear. The physics in this regime is not. There is one more feature of the Kerr equations that I want to walk through, because it is the deepest and the most speculative part of the journey. If you pass through the inside of the ring singularity, in the clean mathematical picture, you arrive in a region of spacetime that has a property no other region in the universe has. The radial coordinate, the distance from the ring, takes on negative values. Negative radius. That is what the mathematics says. On the other side of the ring, the radial coordinate is less than 0, and the geometry of the spacetime there is different from any region you have ever been in. Some physicists have described the negative radius region as a passage to another universe. The phrase is dramatic, but the mathematics behind it is real. The Kerr solution can be analytically extended past the ring into a new region that has its own geometry, its own gravitational properties, and its own structure. In this region, gravity is, in a sense, repulsive. Objects do not fall toward the ring from this side. They are pushed away from it. If you imagine a Penrose diagram of the maximal Kerr extension, which is a particular kind of spacetime map that physicists use to visualize black holes, the structure that emerges is enormous. It has multiple regions. There is the outside universe you came from. There is the region between the horizons. There is the region inside the inner horizon. There is the negative radius region past the ring. And in the full mathematical extension, there are infinitely many copies of these regions, stacked in a sequence, connecting to other universes in the past and the future, in a structure that goes on forever. I want to be honest about what this is and is not. The full mathematical extension of the Kerr solution is, in the strictest sense, what general relativity says happens past the ring of a perfectly clean, isolated, eternal spinning black hole. The mathematics is self-consistent. The geometry is well-defined. The other universes are mathematically real in the sense that they are part of the complete solution. But no real black hole is perfectly clean, isolated, or eternal. Real black holes form from collapsing stars, and the spacetime of a collapsing star does not include all the regions of the maximal Kerr extension. The negative radius region, the other universes, the infinite stack of connected spacetimes, are features of the idealized solution that, in any realistic black hole, almost certainly do not exist as physical regions you can travel to. What is real is the mathematics. What is not certain is whether any of it corresponds to anything physically accessible. This is one of the genuine open questions in fundamental physics. The Kerr solution, our best mathematical description of a spinning black hole, contains a structure on the other side of its center that suggests something far stranger than emptiness. Whether any of that structure is realized in nature, or whether quantum gravity erases it before it can form, is something we do not yet know. Everything I have just described, the layers of the descent, the swapping of coordinates, the inner horizon, the ring, the negative radius region, all of it comes from a single source. It comes from general relativity, Einstein's theory of gravity, applied to a rotating object collapsed inside its own event horizon. General relativity is one of the most successful theories in the history of physics. It has been tested in dozens of ways, in increasingly extreme regimes, and it has passed every test. It correctly predicts the orbits of planets, the bending of light by the sun, the gravitational redshift of light from massive objects, the gravitational waves from colliding black holes. It is, in the regime of strong gravity at large scales, an extraordinarily accurate theory, but it is incomplete. It does not include quantum mechanics, and inside a black hole, in the regions of extreme density and small distances, quantum mechanics matters. Where general relativity predicts a singularity, a point or ring of infinite density, the real answer almost certainly involves quantum effects that the theory does not describe. The singularity, in any honest assessment, is not a real physical object. It is a sign that the theory has failed at this scale. It is the equivalent of getting infinity as the answer to a calculation. Infinity is not a number. Infinity is the calculation telling you that you have asked it to do something it cannot do. The same thing is true of the Cauchy horizon, and of the closed time-like curves, and of the negative radius region past the ring. These are all features of a theory that is, in this regime, incomplete. They are predictions that may or may not survive the eventual development of a full theory of quantum gravity. Quantum gravity, if we ever have it, is expected to do several things. It is expected to remove the singularities, replacing them with finite, well-defined regions of extreme but bounded density. It is expected to either confirm or destroy the Cauchy horizon as a real feature of black holes. It is expected to settle, one way or the other, the question of whether the negative radius region is physical. We do not have quantum gravity yet. We have candidates: string theory, loop quantum gravity, causal set theory, asymptotic safety. None of them is fully developed. None of them gives a clean, agreed-upon answer to the question of what is at the center of a spinning black hole. In some versions of loop quantum gravity, the singularity at the center of a black hole is replaced by a small, finite region of extreme but bounded density, sometimes called a Planck star. In that picture, anything that falls into the black hole eventually bounces and comes back out, although the timescale for this to happen is so long, in our reference frame, that it might exceed the age of the universe. In some versions of string theory, the interior of a black hole is replaced by a complicated structure of strings and brains, sometimes called a fuzzball, that has no sharp horizon and no central singularity at all. In other approaches, the question of what is inside is reframed entirely, and the interior is treated as an emergent description of degrees of freedom that live, in some sense, on the horizon itself. These are all candidate descriptions, and none of them has been verified. They differ from each other in significant ways. They make different predictions, in principle, for what would happen during the formation, evolution, and eventual evaporation of a black hole. Some of those predictions might one day be testable, although the tests would require either observations of black holes that are vastly more detailed than anything we currently have, or laboratory experiments that probe regimes far beyond what is currently possible. What we have, instead, is general relativity, which is an extraordinarily good theory that breaks at the center, and a sense, increasingly shared among theoretical physicists, that the breakage is telling us something. The center of a spinning black hole, mathematically, is the place where our best theory of gravity reaches the edge of its own validity. It is, in a real sense, the place where physics ends and the unknown begins. So what is at the center of a spinning black hole? Let me give you the most honest answer I can. In the clean Kerr metric, what is at the center is a ring singularity, a one-dimensional ring of zero thickness and infinite curvature, lying in the equatorial plane of the rotating black hole. Around the ring, the geometry of spacetime allows closed time-like curves and, in the full extension, passage into a region of negative radius that is mathematically connected to a sequence of other universes. In any real black hole, that idealized solution is destroyed before you ever reach the ring. Mass inflation at the inner Cauchy horizon turns that horizon into a curvature singularity, a wall of infinitely blue-shifted radiation, which is what actually kills any infalling observer. The clean ring you might see in textbook diagrams is not, in any real sense, accessible. In the deepest sense, what is at the center of a spinning black hole is a place where general relativity stops, giving us reliable answers. The theory predicts certain things, and those predictions are mathematically consistent, but they are predictions made in a regime where the theory itself is known to be incomplete. The center is not a location. It is a horizon of knowledge. It is the boundary past which our best current theory of gravity tells us, honestly, that it cannot say. This is what makes the journey through a spinning black hole genuinely terrifying, in a way that has nothing to do with horror or dramatic imagery. The terror is that the universe contains regions where the laws of physics, as we currently understand them, simply stop working, not because we have not looked carefully enough, but because the structure of the equations themselves is telling us that they have run out of road. There is something at the center of a Kerr black hole. We can describe it mathematically, in our best approximation. We can run simulations, draw diagrams, write equations. We can predict, with some confidence, what would happen at each layer of the descent. But we cannot tell you what it is, because the theory we are using does not know, and the deeper theory that might know does not yet exist. The center of a spinning black hole is not a place. It is the edge of our map of reality. We were not wrong about black holes. We were wrong about how cleanly we could understand them all the way down. The first picture, the Schwarzschild picture, was beautiful in its simplicity. A point at the center, a horizon around it, a one-way trip from the outside to the singularity. That picture is probably correct as a rough sketch of what happens inside a non-rotating black hole in the idealization. But real black holes rotate, and rotation, it turns out, changes everything about the inside. It splits the horizon into two. It swaps space and time, and then swaps them back. It turns the singularity from a point into a ring. It opens the door to closed time-like curves and negative radius regions and a mathematical structure that, taken at face value, suggests passage to other universes. And then, in any realistic black hole, mass inflation destroys most of that structure before any traveler could ever reach it. The lesson, I think, is not that the inside of a black hole is simple, or that it is incomprehensible. The lesson is that the inside of a black hole is, right now, the place where our current physics is being tested most severely, and where the gaps in what we know are showing up most clearly. Every layer of the descent reveals something that the simpler models did not predict. Every layer pushes the edge of the theory a little further. The next time you look up at the night sky and think about the black holes that lie at the center of every galaxy, and the smaller ones scattered through every spiral arm, remember that each one of them, almost without exception, is spinning. Each one of them has an ergosphere, and an outer horizon, and an inner horizon, and somewhere inside, a ring of curvature that the equations of general relativity describe but cannot fully explain. Each one of them is, in a real sense, a region of the universe where the laws of physics start to fail. We made a map. We followed it as far as it goes. And at the center of every spinning black hole, the map runs out, and we are left with a question we cannot yet answer. How incredible is that? Good night.